Okay, so now let's see how to use the central limit theorem to come up with a confidence interval. So remember, the sample mean is a random number. How different could it have been? We've seen one way of figuring out how different it could be when we studied the bootstrap, right? So we used the bootstrap, we generated a bunch of different bootstrap samples, calculated the sample means on each, and then saw the distribution of the sample means. And then we used that to construct confidence intervals, intervals which contain 95% of the bootstrapped sample means. But it turns out we can use the CLT, the central limit theorem, when we're interested in the sample mean in particular. And it's computationally cheaper. We don't need to go out and get a bunch more random samples. The central limit theorem is kind of a magic bullet here in the sense that it lets us know what that distribution will be without having to run the bootstrap. So let's start off by going back to what we did a couple of weeks ago by running the bootstrap. So let's run the bootstrap for the sample mean of flight delays. Here's what we do. Remember, I gather a first initial sample, so I'm gathering 400 flights randomly. And then I'm going to resample that sample with replacement 5,000 times. Each time I calculate the sample mean, and I append that to an array of bootstrap means. So let's run this. It'll take a second, as always. Okay, great. So let's visualize the distribution that we got from the bootstrap. Here's what we have. Okay, so here were the sample means that I got in each of my 5,000 trials put into a histogram. So it's centered at around like 12 or so, but notice it has sort of a bell shape to it. It looks kind of like a normal curve. Let's use the bootstrap to construct our 95% confidence interval. So remember, the way that we do this is we compute percentiles, the 2.5th percentile and the 97.5th percentile. That'll give me an interval that contains 95% of the data. So we run this, we get our 95% confidence interval. It says that we're 95% sure that the sample mean, we're 95% sure that the population mean falls within this interval, 9.9 to 15. Okay. And so here's what our confidence interval looks like on our histogram of bootstrap means. Okay, so that's review. Let's think about what the bootstrap gave us. Okay, so we used the bootstrap to figure out how different the sample mean could have been. In other words, what's its distribution? Okay, but do we need to use the bootstrap here? Because we have the central limit theorem. The central limit theorem tells us what that distribution is. It says it's normal, it's approximately normal, and it's centered at the population mean, and its width is the population standard deviation of the square root of the sample size. So the point here is that we don't need the bootstrap to figure out what that distribution could look like. Let's just use the central limit theorem directly, and then we'll use it to construct confidence intervals. Once I know the shape of that distribution, I can construct a 95% confidence interval. Now, we're stuck for a little bit. If you might have been wondering, so the central limit theorem tells us it'll be normal, and it says that it's centered at the population mean, and its width is the population standard deviation over the square root of the sample size, but I don't know the population mean, and I don't know the population standard deviation. And that's exactly right. We don't know these things. If we did, we wouldn't be doing any of this. But we can kind of be a little hand wavy for a moment and say, well, okay, I don't know the population mean, but the sample mean's probably close to it, right? And I don't know the population standard deviation, but if I calculate the standard deviation of the sample, that's probably close to it. So I'm going to replace everywhere I see population in the central limit theorem, I'll replace it with sample. So I'm going to draw a normal curve, and instead of centering it at the population mean, I'll center it at the sample mean. Okay, yeah, that's wrong, but it's close. Statistics is full of kind of these things which, yeah, they're not exactly right, but they're going to be close, and you can rigorously calculate, how close they're going to be in a certain probability. Okay, so it's probably going to be close to the normal, to the population mean, and so this curve is roughly going to be centered at the right place. Okay, it doesn't need to be exactly at the population mean, because if I shift it a little bit, it's a curve, it's a distribution, it's not an exact answer, it's kind of a interval of answers, right? So it doesn't matter that it's right on. Okay, so instead of the population standard deviation, we'll use the sample standard deviation. So remember, the population, that's a histogram that we don't have access to. That histogram has a certain standard deviation. Okay, what I'm talking about here, I'm going to go way back here. This is the population distribution. It has some standard deviation, even though it's not a normal distribution. It has a standard deviation, and I don't know it. What I'm going to do is I'm instead going to calculate the standard deviation of this distribution, the sample, which I have, and it'll probably be pretty close. Okay, so let's go back here. We're going to use these sample quantities, these sample statistics, in the central limit theorem to plot our normal curve. So let's go ahead and do it. I'm going to draw the normal curve. Okay, get a lot of data back here. And here's what I get. So I plotted this curve. It's a normal curve centered at the sample mean, and its standard deviation is the square, or the sample standard deviation over the square root of the number of samples. And what you'll notice here is it pretty much describes that blue bootstrap distribution pretty well. Okay, so I'm plotting here on this figure two different ways of figuring out how different the sample mean could have been. The first way was with the bootstrap, and I had to run 5,000 bootstrap samples, and it took a few seconds. Okay. The second way was just with the central limit theorem. All I had to know was the sample mean, sample standard deviation, and it was instant. I calculated that curve. Okay. Now you might say a few seconds, that's not that big of a deal, but if I had a larger sample, the bootstrap would have taken quite a bit longer. Okay. So let's try to compute the confidence interval now. So remember, what I'm trying to do, excuse me, what I'm trying to do when I compute a confidence interval is I'm trying to figure out what's the bulk of the distribution. With the bootstrap, I just say, okay, let's compute the percentiles that give me an interval that contains 95% of the data. Now, with the normal curve, we know how to compute percentiles in some sense, but we might have to remember exactly what that is. Remember that for a normal curve, 95% of the area, roughly 95% of the area, falls within 2 standard deviations of the mean. Okay, so remember, this is kind of like if I go back and I use SciPy Stats norm CDF and I do 2 minus -2, I'm going to get 95%. Okay, it's going to give me roughly 95% of the area under the normal curve. Okay, so this tells me how to compute a 95% confidence interval. Okay, I say the upper bound of the interval is the mean plus 2 standard deviations. Okay, and then the lower bound is the mean minus 2 standard deviations, and that'll contain 95% of the area of the curve. Now, we have to be very careful here when we use the term standard deviation. What standard deviation? Because there's so many standard deviations right now. There's the population standard deviation, there's the sample standard deviation, there's the standard deviation of the distribution of the sample mean. Which is it? It's the last one. Okay, it's the standard deviation of this curve. Okay, this distribution is the distribution of the sample mean. I want to know how wide this is. That's what the central limit theorem tells us. Central limit theorem says it's the population standard deviation over the square root of the sample size. Here we use the sample standard deviation. Okay, so the width of this is going to be sample standard deviation over the square root of the sample size, and that is the quantity that we're referring to when we use standard deviation here. Okay, so look at how I'm calculating this. I'm finding the right interval by taking the sample mean, and I'm adding 2 standard deviations, where a standard deviation is this whole thing here. It's the standard deviation of the sample over the square root of the sample size. Okay, and then for the lower bound, I'm just subtracting that same quantity. So I do that, I get 9.8 and 15. So you'll notice that, plot the confidence interval here, it looks pretty similar to that bootstrap confidence interval I had previously. Okay, so let's compare that. They're pretty much right on top of one another. The bootstrap confidence interval is green. It's the one on the bottom. It's almost exactly the same as the normal confidence interval. But I got that blue confidence interval without having to run the bootstrap. I saved myself a lot of computation. Okay, so here's the key thing. If I want to compute a 95% confidence interval for the population mean, here's the formula. I take the sample mean and I add and subtract twice the standard deviation of the distribution of the sample mean, which is told to us by the central limit theorem. It's the sample standard deviation over the square root of n. This is an approximation, but pretty much everything in statistics is an approximation, okay? Now, I'll point out here, all of this is for the sample mean, okay? To give some context, the bootstrap is useful, okay? But when it comes to the sample mean, we have a better tool. The central limit theorem is talking only about sample means and sample sums, but we're usually working with sample means. If I start talking about something else like the median flight delay, the central limit theorem doesn't tell us anything. It's not about the median, it's about the sample mean. It's about proportions, okay? So if I'm trying to figure out how different the median could have been, I'm going to go back and use the bootstrap. The bootstrap applies there to almost any sort of statistic except for things like the maximum and the minimum. The bootstrap is very general. But in the specific case that I'm working with the sample mean, I'm going to use the central limit theorem. It's just easier and faster.